Hello again. Here we are in the second part of our section 6.1 and 2 slides. The corresponding section of the textbook for today is section 6.2. We're looking at inference for the difference of two population proportions. Let's give ourselves a research question. Think about the Georgetown College population. Who's more likely to believe in love at first sight? A guy or a gal? And we'll use the familiar M111 survey data to investigate the question. So when you look at the view of the data or read the help, you'll find two variables that are going to be of interest. One is the sex of the person. Think of that as the explanatory variable that might affect their views on whether or not there's such thing as love at first sight. That's recorded in the love_first variable. We'll think of that as the response variable. So it's a two-variable situation here. So first of all, what did the data say? Again, back from early in the course, we can make a tally of love first broken down by the grouping variable sex, as long as we say that those variables live in the M111 survey data frame. And we find the following where I'm waving my mouse. And so of the 40 females, we find that nearly half of them believe in love at first sight, but of the 31 females in the survey, of the 31 males in the survey, a mere 8 believed in love at first sight. This seems like a kind of a big difference between the two sexes. But let's see if we can make some confidence intervals and hypothesis tests to nail down whether that difference we see in the data really should count as strong evidence for some difference out there in Georgetown College as a whole. So the fact is, although we have Georgetown College as one population, for this problem, it actually breaks down into two populations: the population of all Georgetown College females and the population of all Georgetown College males. And because there's two populations, there's two population proportions that we're interested in here. Let's define P1 to be the proportion of all Georgetown College females that believe in love at first sight. That's a number that we don't know. Let's define P2 to be the proportion of all Georgetown College males that believe in love at first sight, another number that we don't know. But if you think that males and females out in the population are equally likely to believe in love at first sight, then you would think that P1 is equal to P2. And a way of expressing that belief is that the difference between P1 and P2, P1 minus P2, equals 0. That's going to be our null hypothesis. Remember, the null hypothesis always says that there's a specific value for a parameter out there. Well, now it's giving a specific value for the difference of these two parameters. And it's sort of the uninteresting case. No interesting pattern out there, no difference between the sexes, nothing to see here. And the alternative hypothesis just disagrees with that. And so it's saying that either females are more likely if P1 is bigger than P2, or females are less likely if P1 is less than P2 to believe in love at first sight. So the Klopper-Pearson methods are not available for the difference of two population proportions. There just ain't no such methods. So we're going to fall back on another test, another function in the TigerStats package called proptestGC. And its syntax is really similar to, its syntax is similar to, but with some differences to tally. What you're going to do is you're going to do a twiddles and then the explanatory grouping variable. Put that first. Then a plus, and then your response variable second. And then you need to say that those two variables in that formula above live in the M111 survey data frame. Now, you've been counting up how many people of each sex believe in love at first sight. So you've been counting who said yes. Remember, when you look at the view in M111 survey, people said yes or no to the love at first sight question. So you need to tell R that you're counting up the yeses in that love first column. So put it in quotes and say success is yes. Now, you've also defined two population parameters. And the P1, the first parameter, was for that population of all Georgetown College females. The second was for the males. So you need to let R know that that's how you're thinking about things. And the way you let it know is this parameter first, you set it to whichever value in the explanatory variable goes with the first population. So take the female value and put it in quotes and let that be first. The P signals that you plan to ask for a test of hypothesis, and you put in the null value. The null value here is 0 because the null hypothesis thinks the difference in proportions is 0. And for fun, we're asking for a graph of the p-value. Usually, once we get enough experience, we don't ask for that. So probably a good idea to copy, paste, run, and take a look in RStudio. There it is, in the console. So let's make it big to see the whole thing. And it's actually a little bit more than can cover one screen. Starts here, ends way down here with the p-value. So we'll take a look at these results bit by bit. It starts off with just basic descriptive results to get you set. And so it repeats essentially the tally that we made earlier in this little table here, but it's focusing on the yeses as what you count up. 18 out of 40 females said yes. 18 out of 40 is 45%. That would be our best guess at the percent of females in the population that believe in love at first sight. 8 out of 31 males believed in love at first sight, 25.81%. That would be our best guess at the percentage of males in the population who believe in love at first sight. Now, right underneath it, though, there's a warning. I mean, it's like we're just getting started. We're setting up, we're looking at our data, we're thinking about setting up null and alternative hypothesis, and boom, we get this warning. In at least one of the two groups, number of successes or number of failures is below 10. Well, yeah, look at that, the 8 there. The normal approximation for confidence intervals and p-value may be unreliable. So let's make sure we know what's going on here. This has to do with the check step when you're making a test of hypothesis or a confidence interval. We're not using those Klopper-Pearson methods. The methods in proptestGC are relying on the fact that the binomial random variables for the number of guys and the number of gals who said yes, that they're approximately normal. And because of that, because we're back to the normal approximation, then we have to think about that success-failure condition in the textbook for a binomial random variable to look approximately normal. Now, proptestGC, basically it checks that success-failure condition for you, and if the condition is not met, it issues the warning that we just saw. And so if you see that warning, you really need to take a close look at your tally again and make sure you know what's going on. There were 18 yeses in our first sample, the females. That's at least 10. We're okay there. But the number of failures was the number of females that were asked the question, which is 40, minus 18. That's 22. Well, that's also bigger than or equal to 10. we're okay there. There's 8 males who said yes. Oh, that's less than 10. That's going to be a problem. Now there's 31 minus 8 males that said no, that's bigger than or equal to 10, that's no problem. So it's really down to just that one of the 4 available numbers in the success failure conditions for the 2 binomial random variables. It's less than 10. It's not a lot less than 10, and some of the others were a lot bigger than 10. So we're not quite safe to trust our results according to the success failure condition. If I were doing this in a professional setting, I would think about some other statistical methods that could be used here other than proptestGC. But since we're learning how proptestGC works, why don't we just proceed and pretend it was okay? We won't tell anybody. So we head down further into the work. Let's take a look at that output. We just blow past this warning here, and let's do some inferential results. What's our best guess at the value for P1 minus P2? Well, we would just take the P1 hat and the P2 hat, the two sample proportions, the 45% and the 25% up here, and we subtract them, and you get 19.19%. Our single best guess is that females are more likely to believe in love at first sight than males by a margin of 19.19%, but that's just a point estimate. And it's subject to all of the chance variation that comes when you sample. The standard error here for P1 hat minus P2 hat says how much it's liable to be off from the real P1 minus P2. And it could easily be off by 11% or more. So this slide gives you the background on those 2 lines in the output. And sure enough, the P1 hat minus the P2 hat really is just the 2 population proportions subtracted. Now let's take a look at that confidence interval that comes right underneath the point estimate and the standard error. This is a 95% confidence interval for P1 minus P2. And it goes from minus 2.5% to positive 40%. So what does that mean for us? Well, our standard interpretation is that we're 95% confident that P1 minus P2 is somewhere between minus 2.5% to really rounds to more like 41%. Now, remembering that P1 was defined to be the proportion of gals who believe in love at first sight, and P2 is the proportion of guys who believe in love at first sight, then negative values for P1 minus P2 would indicate that P1 is less than P2. And that would mean the proportion of guys that believe in love at first sight is bigger than the proportion of gals. Now, this interval contains 0, so it's got some negative values in it. Not a lot, just the values from minus 2.5% to 0, but they're there. They're in the interval, so they're reasonable values that somebody could believe in, even after they've seen this data. And so, because that null value of 0 is in the interval, allowing some negative values to creep into its left, we cannot rule out the null hypothesis using this confidence interval, It would still be reasonable to believe that guys are more likely to believe in love at first sight, and that we just got a kind of unusual sample. We can see the same thing if we go to the test of hypothesis. And in the output, the test statistic is given down near the end. It is a z-score, and we'll take a look at the formula here. A z-statistic is always your point estimate minus the null value over the standard error for your estimator. So our point estimate is the difference in the two sample proportions. The null value this time is 0. And the standard error is the standard error for P1 hat minus P2 hat, which has a complicated formula that you don't need to remember for this course. But when you do the division, and R does it for you, it turns out to be about 1.726. So what that test statistic is saying is that the difference in sample proportions was about 1.7 standard errors above what a believer in the null hypothesis would be expecting to see. A believer in the null figures that P1 hat minus P2 hat should come out to be near 0, give or take some for chance error. It came out to be 1.72 standard errors above 0. Well, how unlikely is that to happen if the null is correct? That's where the p-value comes in, and in your output, it's way down at the bottom. So that's about 8.4%. So the way you interpret it in a complete sentence is if the null is correct, guys and gals are equally likely to believe out there in population, then there's about an 8.4% chance of getting a test statistic that's at least as far from 0 as that 1.72 that we actually got. So a graph of it, we asked for one, and it's shown here that 8.4% is divided evenly between the area after our test statistic and before minus our test statistic under a normal curve. Just remember, this time we slightly failed the success failure condition. And so the real distribution of the test statistic might be significantly different from a standard normal distribution pictured here. And therefore, the statement of the areas underneath the curve might be a bit off. That 8.4% could be somewhat off. But pretending that everything's okay, we just compare it to our standard cutoff alpha of 0.05. It's bigger. 0.084 is bigger than 0.05. So we're going to fail to reject the null hypothesis. This time, the data don't quite provide strong evidence that Georgetown College males and females differ out there in the population in their belief in love at first sight. So what you should notice here is that in hypothesis tests for the difference of two proportions, we really are back to the full 4 standard steps of hypothesis testing. You got your preparation step where you take a look at the data and set up your hypotheses. You've got your check step, and that's the success failure condition in addition to making sure that you really took 2 independent random samples from your 2 populations. proptestGC is going to do that success failure check for you, but you have to read the output to make sure you passed. And then to calculate, proptestGC is calculating the z-statistic for you, calculating the p-value for you. But it's up to you to make the conclusion. You're the one who has the alpha value in mind, so you need to make the decision about whether or not to reject the null. You need to write up that simple conclusion for the test. Let's do another example. I'd like to do one where you don't get it from data in a data frame that's provided for you on RStudio. Let's just get it off the web where we have just summary data. So I took a look on Gallup.com a little bit, and looking back at 2019, in June of 2019, people were debating about whether they wanted to impeach Donald Trump, and about 45% of 1,500 Americans who were sampled by Gallup approved of impeaching Donald Trump back in June 2019. And then the big scandal broke about the the Ukrainian situation where Trump was basically trying to blackmail Ukraine into doing some investigations of Hunter Biden in order to get some military aid for his war against Russia. And so all that came out, and by October 2019, Gallup ran another poll. This time, 1,526 people are in the poll, and 52% approved of impeaching Trump. That's the poll we discussed in the previous part of the slides. Well, what we got here is, you can think of it as two populations. The population of all Americans in June of 2019 and the population of all Americans in October of 2019. And you've got two different random samples taken from these two populations. And you're looking at this difference in the sample proportions, 52% versus 45%, and you're saying, wow, that seems like a big jump. Does that data provide strong evidence that support for impeaching Trump has increased out in the population since all the revelations about Trump's phone call with the Ukrainian leader? So thinking about your two populations, you can set up two population proportions. P1 is the proportion of all U.S. adults in October 2019 who support impeachment. P2 is the proportion of all U.S. adults in June 2019 who support impeachment. When you set up, it doesn't matter which population you put first, but you just need to keep in mind what you chose first, and so that you can tell R what you want to be first. The null hypothesis is just going to say P1 minus P2 is 0. So it's the uninteresting hypothesis that impeachment support in the American public has stayed the same between June and October, and that 52 versus 45% we saw in the samples is just due to chance variation in the sampling process. And the alternative hypothesis is saying, no, that observed difference is too big to be explained that way. There must have been a shift in the population. So if you're going to use proptestGC to help you out with confidence intervals and hypothesis tests, you're going to have to find out how many people actually said yes in each sample. Yes, we ought to impeach Trump. So you'll have to use your sample proportions for it. Out of the 1,526 people in October, 52% said yes. So do that multiplication, you get 793.52, which I'm rounding off to 794. There were about 1,500 people in the June sample, 45% yes, said yes. That product is 675. So I'm figuring 675 people said yes in that poll. And then you head to proptestGC, but you don't use the formula data interface, you use a summary data interface. The X parameter here has to be the concatenation of the two counts of yeses. The count in the first sample, 794, the count in the second sample, 675. The N parameter gives the two sample sizes. It's the concatenation of the size of the first sample and the size of the second sample. And you got to make sure they go along with each other. The first is the October sample. The October sample. The second is the June sample. The second is the June sample. And if you want the hypothesis test, you've got to provide the null value to R. You do that with the parameter P. So I'm going to go ahead and copy paste and run this. And here we go. So inferential procedures for the difference of two proportions, results taken from summary data. So I'll just pop back here since slides don't show it too much. You still are given descriptive results, even though you know them already. So you got your yeses and your sample size, your yeses and your sample size for the two for the two samples. And so you see the difference in the sample proportions here. And let's go back again. The difference in the sample proportions, the 52% minus the 45%, comes to about a 7%. That's your best guess at what P1 minus P2 is. But that guess could be off by about 1.8% or so. Oh, and here's a confidence interval. It goes from 3.5% roughly to about 10.6%. We're 95% confident that P1 minus P2 is really in there. Notice that all of the values in the interval, everything from this number to this number, is a positive number. So there are no negative numbers in there. It would not be reasonable to believe, based on this data, that support for Trump's impeachment has declined. It would only be reasonable to believe that it has increased. And then we have our test of significance with the hypotheses laid out. Now, the last bit we'll address through the slides. The test statistic got computed for you. The difference of 7% that we observed between the two samples is 3.879, about 3.9 standard errors above what the null was expecting it to be. The null thinks that P1 is P2. So it's figuring P1 hat ought to be about P2 hat. So it's figuring the difference in the sample proportions ought to be around 0%, give or take some, for chance error, the sampling process. But this was way above what the null was expecting. How unlikely is this? If the null is right, that's the p-value. So that is about 1 in 10,000. Incredibly low p-value, certainly less than 0.05. So I would be rejecting the null hypothesis here. And my conclusion is that based on the data, there's really strong evidence that support for impeachment increased out there in the population over that time period. So it's your turn now. You'll have the assignment to do a DA on section 6.1 and 2. Get to work on it as soon as you get it. And remember to ask early and ask often on the discussion boards. See you soon.